In this video, we will discuss section 26, harmonic functions. First, we have a definition. A real valued function defined on xy plane or a subset of xy plane, say h, the real valued function h of two variables x and y is said to be harmonic in a domain. In a domain means in a subset of xy plane if throughout that domain it has continuous partial derivatives of the first and second order and satisfies the partial differential equation hxx of xy plus hyy of xy equal to 0. That is, if this x is a function from a subset D of xy plane, say R cross R, you can call it as R cross R, subset of R cross R to R. So this is a function from a subset of R cross R to R. Then the all partial derivatives, say hx, hy, hxx, hyy, and hxy, hyx, all the second order partial derivatives should be continuous throughout that domain. And we have dou h by partial derivative of h with respect to dou square h by dou x square plus dou square h by dou y square should be 0. At all points, if these two conditions are satisfied, then this h is said to be harmonic. So this is the definition of a harmonic function. So there is a close relation between harmonic functions and Cauchy-Riemann equations. So we will discuss that in this section as theorem 1. Before that, we will be discussing an example of harmonic function. Consider the function t of xy, that is equal to e power minus y sin x. So this is a function, this t is a function from the subset of xy plane defined using these two inequalities. This is called a vertical semi-infinite vertical strip, 0 less than x less than pi, y greater than 0. So that denotes this vertical strip. And if we call this as some e, then this is a function from e to r. Okay, so the real value function. And if we consider this t of xy and write the partial derivative tx, which is equal to e to the power minus y times cos x. This cos x is the derivative of this sin x. And ty is minus e to the power minus y times sin x itself, and we can write txx. So there is a derivative of this function with respect to x again, that is minus of e to the power minus y sin x, because the derivative cos x is minus sin x. So we write txx is equal to e to the power minus y times minus sin x, and tyy, that is the derivative of this with respect to y. So that is tyy is equal to derivative of e raised to minus y is again minus e raised to minus y. So that will be e raised to minus y times sin x. And finally, we can write txy or tyx. In this case, both will be the same. Txx can be obtained from this expression by differentiating with respect to y. That will be minus e to the power minus y cos x, or the same thing can be obtained from this expression by differentiating this with respect to x. So that will be minus e to the power minus y times cos x. So that will be both are equal. So this is txy, or you can consider this as tyx as well. And if we look into all these partial derivatives, first order and second order partial derivatives, we can see that all these functions involves exponential function as well as trigonometric function sin x and cos x. So all these functions are continuous as well. Now you consider the equation txx plus tyy, that is minus txx is minus of e to the power minus y sin x, and tyy is equal to e to the power minus y times sin x, and finally the sum is 0. So it shows that all the partial derivatives, both first order and second order, are continuous, and this t satisfies the Laplace equation, say txx plus tyy at every point of this vertical slip. then we can say that this t is an example of harmonic function. So you can consider this an example of harmonic functions, and you will get more examples if we consider an analytic function, because in the next case we will show that the components of the analytic function f of z are always harmonic. Okay, that means we have theorem 1. Theorem 1 says that if a function f of z is equal to u of xy plus iv of xy is analytic in D, then its component functions u and v are harmonic in D. That means if we consider the function f of z, f is equal to u plus iv, then we know that since this f is analytic, then f is differentiable throughout that D. That means if this is analytic, implies u and v are u as well as v are differentiable. This was the first theorem we have discussed in the beginning of section 1, and from this you can get all the partial derivative exist, and we know that this u and v are differentiable means all the partial derivative exist and all are continuous as well. So we are not going to prove all these things, so we can just write that the components of f are differentiable, consequently all partial derivatives are continuous. These are continuous. And finally, if we consider u, then we know that ux equal to vy and uy is equal to minus vx because of Cauchy-Riemann equations. This is a consequence of a necessary condition of a differentiable function. Then we have ux equal to this, uy is equal to this. Now what is uxx? Uxx is nothing but vyx. Similarly, what is uyy? Uyy is nothing but minus vxy. But we know that since this v is a continuous function, being it is a differentiable function, continuous function, we have vxy is same as vyx. Okay, so this is Fibini's theorem. You might have seen this theorem in your second or third semesters, and from this you can say that uxx plus uyy is equal to vyx minus vxy. But we know that these two things are same. That is equal to when that means this is equal to 0, which implies u is harmonic. U is a harmonic function. Similarly, you can prove the other component v, because by choosing v by y from this and vxx from this. Okay, so the same equation holds for v as well. So we shows that the components of analytic functions are always harmonic. Next we have a definition of harmonic conjugate. If two given functions u and v are harmonic in a domain D, and their first order partial derivatives satisfies Cauchy-Riemann equation throughout D, then u is said to be a harmonic conjugate of u. Okay, so this is the definition of a harmonic conjugate of a function u. In order to get the harmonic conjugate, we will have this u and v, and this u and v satisfies the equations, and we know that this u and v are harmonic functions. As a consequence, we can get all the partial derivatives of u and v continuous, and u and v satisfies the equations. Okay, if this happens, you can easily say that this u and v, if this v is a harmonic conjugate of u, then we have ux equal to vy, and uy is equal to minus vx, and all partial derivatives are continuous. Then using the sufficient condition for the differentiability, we can say that this would imply that this would imply that u plus iv is analytic. In order to get u plus iv is analytic, the sufficient condition is u and v should satisfy the equation, and all the partial derivatives, first and second order partial derivatives of u and v should be continuous throughout a domain. So So if V is a conjugate of harmonic conjugate of U, then you can easily get U plus IV is analytic. Okay, so next theorem gives the characterization of this harmonic conjugate. That means the theorem states that a function f of z equal to U plus IV is analytic in a domain D if and only if this U and V are harmonic conjugate. Okay, we already discussed that one part of the theorem. If U and V are harmonic conjugates, then U plus IV is a analytic functions. Okay, we will prove the converse as well in the next theorem. A function f of z is equal to U plus IV is analytic in a domain D if and only if V is a harmonic conjugate of U. So one part is trivial, that is if we assume U and or V is a, if V is a harmonic conjugate of U, in the definition itself you will get U x equal to Vy and Uy is equal to minus Vx. This is the definition of harmonic conjugate. UV satisfies CR equations, and U and we have U comma V are harmonic functions. Since this is harmonic, then all the partial derivatives of U and continuous. So whenever all the partial derivatives of U and V are continuous along with CR equations, we will get U plus IV. U plus IV is analytic. Consequently, we have F is analytic. So if V is a harmonic conjugate of U, then f of z equal to U plus IV is analytic. Conversely, we assume that F is analytic. Then conversely, F is analytic implies U and V satisfy CR equations, and U and V are differentiable, implies this all partial derivatives of U and V exist and continuous along with by the previous theorem, by theorem 1, we have U and V satisfy CR equations. Okay, then we can consider V is therefore V is the harmonic conjugate of U. So this proves theorem 2. And in this section, some examples are discussed which deals with to find the harmonic conjugate V of U. So example 5 is very important, so please go through it. So try to solve this problem. Find harmonic conjugate of U of xy, which is equal to y cube minus 3x square y. So first of all, you have to verify that this U is harmonic, then only you will get the harmonic conjugate as well. So in order to verify this U is harmonic, then you need to verify that all the partial derivatives of U of x, y exist. So that is trivial because this is a polynomial in x and y. So all the partial derivatives is again polynomials. So U of x, y, all the derivatives of all the partial derivatives U of x, y is again polynomial, hence they are all continuous as well. And you can easily verify that U xx plus U yy by simply from this expression itself, the derivative of this function with respect to x is minus 6xy because of the first term is constant, and similarly uxx is equal to minus 6y. Similarly you can write uy is 3y square minus this 3x square, and uyy is equal to derivative of y with respect to this. That is again this is 6y. When you add or sum up these two quantities, you get 0. So you can easily verify that this u is a harmonic function, and now you can get the harmonic conjugate of this. If this v is the harmonic conjugate, of u, then you know that f is equal to u plus iv is analytic. Okay, or vx can be obtained by, you can easily verify that what is vx of xy. Vx of xy is same as minus uy of xy, and minus uy can be obtained from this expression. So you can write this as minus of 3y square minus 3x square, and from this you can easily, this is a partial derivative of v with respect to x. Okay, so if you integrate partially with respect to x, this will become v of xy, and that is equal to, by integrating this with respect to x, you will get minus 3y square x by treating y as a constant, minus this is 3x cube by 3, that will be x cube itself. So plus a function of y, so that is c of some y. So this is since we are treating y as a constant, so in order to add a constant of integration, we need to add a function of y alone. So this whenever you obtain this c of y, you will get v of xy itself. Okay, so in order to get v of xy, you can consider vy of xy, derivative of this function with respect to y, that will give this is minus 6 yx, this is the derivative of y, minus 3y square x with respect to y, that will be derivative y square will be 2y, then that will be minus 6 times yx, and derivative y of the derivative of minus x cube with respect to y is equal to 0, then that will be 0 here, and this is the derivative of c of y with respect to y, so that will give the total derivative c dash of y. So this is, we know that vy is same as, okay, since this u and v are components of a partial analytic function, so vy is same as ux, and ux can be obtained from this, so that is minus 6xy. So by solving this, you will get minus 6yx plus c dash y is equal to minus 6yx. So from this you can get c of y equal to 0, which derivative of this with respect to, total derivative of this with respect to y equal to 0, so this constant function. So c of y will be some k. So this becomes v of xy is equal to minus 3y square x minus x cube plus some arbitrary constant quantity k. So now you can say that this function, so here we have plus here because we are collecting minus uy. Minus uy is 3y square minus 3x square times minus 1. So that will be minus 3y square plus 3x square. So we have plus x cube here, so we have plus x cube here, this is x cube rather than x square. So minus 3y square x plus x cube plus c of y, that will become, since c of y is a constant, that will become v of x y is equal to minus 3y square x plus x cube plus an arbitrary constant k. So which shows that this v is harmonic conjugate of u. So with this we can conclude section 26. In the next class we will discuss chapter 3 onwards from section 29 that deals with the exponential function and some examples of other complex functions.